Okay, so here students, we're going to be dealing with linear differential equations. Kindly note, the notations are slightly different because these are not slides which I have prepared. Ma'am Vaishali has prepared them and I'm going to be explaining certain things to you on this. Now just pay attention to all of this. So what we have here is, as we all have seen, we were dealing with an capital, I'll change that, an capital D raised to n plus a n minus 1 capital D raised to n minus 1, so on and so forth, plus dot dot dot, all of this operated on y is equal to q of x. Here in the previous videos, wherever I have written a, ma'am has used k, and wherever there is q of x, she has used f of x. So just different notations, that is all. Okay, but the differential equation is the same. So now moving on, as you see, this is the differential equation which we are going to be dealing with. Now, you all already know how to deal with this differential equation. Okay, so it is wherever you all used to see a naught, a1, an minus 1, it is just another notation given as k naught, k1, kn minus 1, and they are all constants. Okay, and where you all used to see qx, you will be seeing f of x. That's the difference that you see here. That's all. But they mean the same thing. Now, if you look at this portion here, this is nothing but a function of d. Don't you agree? Because see, if you have everything in terms of d raised to n, d raised to n minus 1, you have d. So this is a function of d. So a function of d is operated on y equal to f of x. So a function of d operated on y is equal to f of x. So y becomes what? 1 upon f of d operated on f of x. So to find the particular integral, I'll be using this, y equal to 1 upon f of d operated on f of x. Now, as I mentioned in the earlier video which I sent you all, this f of x can basically be an exponential function, it can be a trigonometric function, it can be anything. So I'm going to be explaining to you all cases. When it is an exponential function, how to deal with it. When it is a sine function, how to deal with it. Okay, so that's what we're going to be learning now. So we move on to this slide. So here, if you notice, I'm looking at a particular integral. I'm finding I have a situation, the case 1, where f of x is e raised to ax. So what will the answer basically be? So when I have f of d operated on y equal to e raised to ax. My yp will be 1 upon f of d operated on e raised to ax. Very simple. What I will do is, wherever I will look at this a and I will replace d by a. So f of d that you see here will be replaced by f of a. So the answer that you will end up getting is nothing but going to be e raised to ax upon f of a. Just look at that. It's very clear. When you have 1 upon f of d e raised to ax, wherever there is a capital D, I will replace the capital D by a. Now there's only one problem that you will face. F of a cannot be equal to 0, then I cannot use this. If f of a is equal to 0, then the denominator goes to 0, which is not defined. So what do we do when f of a is equal to 0? When f of a is equal to 0, this is what's going to happen. We'll have to pull an x outside. We'll have to do 1 upon f dash of d. We'll have to differentiate that function of d and operate that on e raised to ax. So you'll have an x outside, 1 upon f dash of d, e raised to ax. And this will become x 1 upon, again, wherever in f dash of d you see d, you will replace the d by a. So that's going to be f dash of a e raised to ax, provided again that your f dash of a should not be 0. So you'll have to proceed in this manner all the time. Okay, so we'll take an example. Look at this example. This is a problem that's given to us. Now, the solution of this differential equation will be what? Yc plus yp. to get yc, what we will do, we will have to put d square minus 2d plus 10 operated on y, we equate it to 0. Then find the auxiliary equation, proceed, and we will find the complementary function. So up to here we have already done. Now what we are interested in doing is finding the particular integral. So how do we find that? So it's going to be what? What is my first question? What is my f of d in this case? My f of d in this case is d square minus 2d plus 10. So what will my yp be? My yp will be equal to 1 upon f of d operated on e raised to 2x. So that is equal to 1 upon f of d. What is d? D square minus 2d plus 10 operated on e raised to 2x. Now wherever there is a d, you will change it to 2. So what will I end up getting? I'll get 2 square here minus 2 into 2, which is again 4, plus 10. So finally, my f of d becomes f of 2, and f of 2 works out to be simply 10. Wherever there is capital D, just put it as 2. So I'll get 4 here. Here I'll get another 4. So 4 minus 4 is 0, and I'm only left with the number 10. And your final answer, yp will be equal to e raised to 2x upon 10. So therefore, the complete solution will be complementary function plus particular integral, and this is how you write it. Now this was a very simple case where f of d or f of a, or rather f of 2, was not going to 0. You will come up with situations wherein f of 2 goes to 0. Then you will have to use the exceptional rule. So that will be seen in this example. So I would like you all to go through this example, and maybe we can discuss this example eventually.